Welcome to the part 2 of CFD interview questions for the beginners and interns. So in this part, I will be going one level above for the questions and answers which will be asked in the CFD interviews. So let's begin. The next question is type of mesh elements and their advantages. So it is very important parameter which is called as mesh, where we simulate our real life problems in CFD. So the types of mesh elements are tetrahedral, hexahedral, prism and pyramids. So tetrahedral meshes are easy to generate, and when our geometry is very complex, so tetrahedral mesh is preferred. But the hexahedral mesh, which is a brick shaped mesh, is a better accurate mesh. It provides lower numerical diffusion and it also provides you faster conversions, but it is hard to generate because our everyday objects are not in the perfectly brick shaped model. Hence it is always preferred to have the mixed number of hexahedral and tetrahedrals. So then prism layers are used to near walls to resolve boundary layers effectively. So in previous video we saw that why the boundary layers are important and everything. So prism layers are one which are used to resolve these boundary layers. So why the mesh selection is important? Because it will directly impact on our CFD accuracy, time consumed by the CFD solution to solve, and quality of our problems and quality of our solutions. Next question based on the mesh is skewness and orthogonality. So what is skewness? So skewness is measured by how much our element is deviating from its ideal shape. So suppose our ideal shape is rectangle, and if it is getting skewed, then how much it is getting skewed, this is called as skewness. So whenever there is a maximum skewness, then it will cause our simulation to have the very low accuracy and it will cause us instability. That means our solution may diverge. So this is called as skewness. The next question is what is orthogonality? So what is orthogonality is that there will be one vector which is connecting the element centers and the normal vector. So if that vector is perfect, then our orthogonality is good, and it means that we will have a better flux calculations. Hence there are generally limits which says that skewness should not be more than 0.7 and the orthogonality should be minimum of 0.15. Next question is what is mesh independence study? So whenever you are running a CFD, how to be sure that my solution is converged or my solution is perfect? So in this case, what happens is, if you have taken a minimum size of your mesh as a 10 mm, then for the next iteration you will be taking that mesh with a size of 8 mm or 12 mm, then 6 mm. So by performing the final meshes in next iterations, you will be judging that my solution is mesh independent or not. If my values are getting changed over a final mesh, then I have to perform the solution again and again in order to achieve the perfect solution. So by performing the solutions, changing the mesh, it is called as mesh independence study. Next is what is turbulence? So turbulence is flow regime characterized by chaotic irregular motion with eddies and vortices. So the flow which is chaotic, which has a very irregular motion and it is forming eddies and vortices, everything, so that flow is called as turbulence. What turbulence affects is it leads to enhanced mixing, it creates higher drag, and it will give you greater heat and momentum transfer. Okay, so in real world scenario, our most of the flows will be turbulent, which if you consider air flow over an airplane or your water flow in pipe, all the cases in maximum times will be turbulent cases. Hence modeling the turbulence is always the challenge in CFD. So how to model turbulence? Next question is what are RANs, alias and DNs? So RANS is Reynolds average Navier-Stokes model, which takes average effect of turbulence. So in real world there will be DNS, which is direct numerical simulation. So DNS will solve these turbulence scales without modeling or without resolving them or without averaging them. It will directly solve them as accurately as possible, but it has a very high unrealistic computational cost. So hence sometimes it is preferred to use LES. So LES is large eddy simulation. So what is LES? LES resolves large turbulence structures directly, and it models only the small scales. Okay, so it is more accurate, but it is again expensive for the computational cost. Hence RANS is used in general, which averages out the turbulence effect and gives us the accurate solutions, which saves our computational efforts. Okay. Next question is, what is Navier-Stokes equation? So Navier-Stokes equation is the what everything CFD is based on, we can say. Okay, it is a mathematical equation which describes the fluid motion. So it is based on basically Newton's second law to apply to fluid elements and combined with the law of conservation of mass. So there are basically three laws, which is conservation of mass, conservation of momentum, and conservation of energy. Combined all these three laws and you will get Navier-Stokes equation. So it takes account for inertial forces, which are due to fluid acceleration, fluid motion, then pressure forces, viscous forces, and gravity. So these equations are non-linear and they are coupled with partial differential equations. So in real life scenario it is impossible to solve these equations. That's why we are using the CFD softwares to solve them numerically. The next question is, what are limitations of RANS model? So as I said earlier also, the RANS model will assume the turbulence and it will average out this. Okay, so it can cause some of the inaccuracies when we have to I can say we have to analyze the higher separating flows, or where we want to judge the eddies, or in particular how the flow separation is happening and everything. So in some particular cases it will fail to capture that problem. Hence RAM is efficient for in general life purposes, but whenever there comes to some of the specific requirements, then we use the LES model. Next question is, what are eddy viscosity models? So eddy viscosity models that assume turbulence increases the effective viscosity of the fluid, which smoothens the chaotic effects. So eddy viscosity models add artificial viscosity to the flow equations to model turbulent stresses. So which are the eddy viscosity models which we use? Are k-epsilon and k-omega. So question is, common turbulence models and when to use them. So common turbulence model which are available are k-epsilon and k-omega SST model. So k-epsilon model is good for general external and internal force. Okay, it is robust and stable model. On the other hand, there is k-omega SST model. So whenever you want to capture your transition or flows and everything near the walls in the better way, then you will be using k-omega SST model. Then another model is Palat-Almas. This model is simple and good for external aerodynamic flows like aircraft. So choosing the right model, it depends upon our flow type. We want to study the separation or not, what wall effects we want to consider, and our available computational power. Thank you for listening to the part 2. We'll be back with the part 3, and don't forget to like, share and subscribe.